In this video, I'll describe how my solver for FlowFree Shapes works. If you haven't watched this video where I show off its capacities, I'll recommend you watch it. In this video, I'll describe all the steps described here that are written in C#. So let's get into it. So first, I've used forms because it's pretty easy to have a UI with buttons and images to debug and stuff. So if you take a look at forms 1, I first run the test. So when you initialize the program, it runs the test and then it starts a background worker solver that will always check at the screen and try to solve the puzzle, right? So the tests, if you look into Solution Explorer, you'll see a folder called test with images. I'll open it. So those are like the unit tests of my program to make sure it works after modifications. What a test is you load the image, you load the base image, and then you try to solve that base image. Because my solver uses the screen, right? And tries to find out what the puzzle is, right? And then solve it. And if it did solve it, it plays it, right? For the unit tests, it doesn't play it, of course, because there's no cursor to move, right? So what solving a puzzle is first detecting the cells, right? So a cell is one part of the puzzle. I'll open the simplest here. So the cell is one cell. It can have a base color, which is a source, or it can have no color, which is just a standard cell. Each cell has neighbors, so when you run the image detection, it needs to find its neighbors, which it can connect to, and that's pretty much it. Then you call save puzzle because we want to save the puzzle as the before it solved it. So we know that the neighbor detection worked. Then we run puzzle.solve and whether or not it did solve it, and then we save the puzzle another time. We save the solution. So if I take a look at my program here, you see folders with every images of every puzzle. So if I take a look at one, this is the puzzle before solving, right? So we can see each cell with each of its neighbors and the color. We can also see each step of the solver program, right? So we can see its steps to solving it. We can also see the result of the solver, so drawn over the base puzzle. Also, we can see other debugging images from the image processing, right? here is the mask which defines the contours and where the dots color are, so the contours of each cell, and also the color contours output. So after making the mask, we run a contour detection, and you can see here that each cell has a different color than the one next to it, and also that the line thickness is bigger than the circles, because we only care about the cells for this. And also note that the whole puzzle contour has been rejected too. So I'll go into the detector, cell detector. So the cell detector that detects cells, first it um, creates a gray mat because we don't care much about color much when we do our contours. Then we apply a threshold to create a mask. Then we apply that mask. Then we save those. After that, we we run the contour detection. So find contour from cv imgu.cv. After that, we process the contours. So we first make a cluster, a list of cluster, an array of clusters, sorry, which we assign indexes, their areas, and if the area is way too small or way too big, we check its isBad value. Then we also find the biggest cluster. This name might be misleading. Oh yeah. So basically, what if you look at the distribution of blobs on a chart, right? You'll see that around here is the area for a circle, right? Around here is the area for a cell, and around here is like the whole puzzle, right? And you'll see something like this. So up we have a couple of circles, then a lot of cells, and then a single puzzle contour. And what we're interested in is this one. So we call the find biggest cluster because it's the biggest here, like the biggest count of a single cluster, which will then return will then check, like we'll set these as bad and this as bad, so these are okay. We then continue from there. We draw the contours for debug. We then approximate a contour. We apply a poly contour, so we approximate like shapes to simpler shapes, like hexagon and squares. We find the center of the contour and we use the center of the contour to get the pixel of the cell color. We then round the cell color and create a new cell of this cell color with center. Once we've done that, we need to also find the neighbors, right? So if I go back to my contours output, those two are neighbors because one of their sides is next to the other one's side, right? So for each line, we have a list of each line with its index to their cell, right? So if their distances from start to end is less than 12, we skip it because it's 12 pixel long and it's too short, so we just skip it. And then for all the other lines, so line J, we check if they have the same index. If they do, we skip it. If the distances if the distances between the start and end of J is too short, we skip it too. And then we check the distance between the center of one line and the center of the other, and it needs to be less than 30 pixel. 30 pixel is a lot. So imagine here, the center of this line is right here, the center of this line is right here. We check if there are 30 pixel apart or less. And then we calculate the distance to point from IG.center to line IG. So what this does is it's a function that given a line that I'll trace black, given a line and a point right here, returns the orthogonal distance from the line to the point. So it returns that distance, right? So what I'm doing is I'm checking if the distance from the center point of one line to the other is less than 5 pixel, or that the distance from one center to the other line is also less than 5 pixel. If so, well, I add the neighbor. I call cell.addNeighbor from one cell to another. And add neighbors, what it does is that it also add the neighbors to the other neighbor, right? So both are neighbors. Once that's done, we know that the image has been processed. We also remove orphan cells. So we call cell.isOrphan and we remove it. And then we save and we dispose of images of bitmaps. So to solve a puzzle, it's pretty simple. First, it's a recursion algorithm, right? So first, we do a little bit of pre-processing on the puzzle. So what we have to do first is is checking or not is receiving cell dot. For any puzzle, there's always two dots of the same color, right? And each two dots, what I'll do is set one as output and one as input. So I call is receiving. So the one that is receiving is the one that's inputting, and the other one, otherwise, it's output. So that's the preprocessing here. Then I call recurse of 0. Recurse is the main recursion function. You start at 0, so that's like the index of the cell, because I have a list of cells and that's the index. So I check here if it's the end cell. I check if it's valid. Wait, here is one more than the cell count. So I check if every cell is valid. So is valid is like a rule in FlowFree. If you're a cell dot, which means if you're a colored cell, you're valid. If the receiving cell dot is not either you're receiving cell dot, so you don't need to have any connected cell, or that your connected cell is not null, and you're also valid if you're a standard cell if the connected cell is not null, of course, because every cell connects to another one, right? So take for example this cell here. If this is output, well, this connects to this one, and this one's connect to this one's, and so on. Also check once you're on a cell, sorry, it checks is valid. So if it's valid, you go to the next cell, right? Otherwise you try to connect to any of the neighbors, right? You every and any of the neighbors. So you check, okay, if I connect to my neighbor, to this neighbor n, will I tail back to myself? If so, I skip it. If I can connect, so try connect is try connecting, and if it succeeds, it returns true. So once I tried connecting to one, I check if my tail can escape, if my head can escape, and if I'm not tailing back on such cell, and if all these are right, I do recurse of next. Otherwise, I call disconnect. Disconnect is really simple. You just set connected cell to null, and you also change the color back to black. And when changing the color back to black, it propagates forward and then backwards again if it's connected to a colored cell. This could be very well improved, but I'm lazy. And that's the whole recursion algorithm right there. You got it. For the conditions, you have here tailbacks, so it's pretty standard. Tail also. It's very simple optimization. So like for example, if you connect, if the yellow here was to connect to this red here, well, you can see that these two are next to another, and that's illegal in FlowFree when it does that. So simple optimizations like these, so that it can solve very big puzzle very fast. Um, I may have here, look for example this puzzle here. This is the solution. Well, you can see that the rule I just said is valid for any puzzle, and in only 116 steps it solved it. So it's pretty fast. Note that my image processing algorithm uh, did sort the cells from bottom to up and right to left, which is essential for such program. If it wasn't like so, I would have made it sort them in one direction, because it needs the cell order in the list. When you recurse on it, you need to have it sorted from its like position, right? I hope you learned a lot from this video, and that I've explained everything very clearly. And I also hope that this video serves as reference for future programs. Feel free to clone this code and use it wherever you like. Thank you.